Well, for our area roads, it's been busy construction season.
And some work is taking longer than others.
Every year, the United States builds more than 40,000 kilometers of new roads. Nearly 1/3 of them are made from concrete, engineered to last 50 years and carry dozens of tons day after day. But beneath these ordinary-looking highways is a world most people never see. Roadbeds compacted like skyscraper foundations, steel reinforcement placed with centimeter-level precision, colossal paving machines.
We're going to check out this paving spread and explain to you what it takes to pave a road with concrete today.
Stretching dozens of meters long, moving across the site like industrial robots. This isn't simple road construction, it's high-precision engineering on a massive scale. So how do American engineers transform raw stone, steel, and cement into some of the most durable concrete roads on Earth? Overview of concrete roads in the U.S. When people think of roads, most picture asphalt. But across the United States, concrete highways are far more common than many realize. In fact, over 30% of the federal highway system is built using cement concrete. While concrete may not feel as smooth as asphalt, it's often the preferred choice for major routes, and for good reason. Concrete pavements can last up to 34 years, nearly twice the lifespan of asphalt roads. They're far less likely to sink or deform under extreme heat, making them ideal for corridors carrying heavy truck traffic. Concrete construction can move faster. With modern, continuous paving machines, crews can complete 3 to 5 kilometers of roadway per day, dramatically reducing project timelines. Soil preparation, building the foundation. Every concrete road begins with a careful evaluation of the route. Once the alignment is selected, engineers study the terrain to assess the strength and quality of the underlying soil and rock. They determine how much earth must be removed or added and how construction will impact traffic and the surrounding environment. These plans guide key decisions: lane width, road length, and overall design. After plans are approved, construction begins with clearing the site. Vegetation is removed and the roadbed is raised or lowered to match the natural landscape. The soil foundation must then be compacted to support both the concrete pavement and the heavy vehicles that will travel over it. A grader levels the surface while underground utilities, electricity, water, and drainage are installed. On roads without sidewalks, drainage ditches are often built along both sides to manage runoff. Building the road base. Once underground systems are complete, crews construct the road base, the critical middle layer that transfers weight from the concrete surface down into the soil. A layer of large, crushed stone is spread evenly across the roadbed and compacted using vibratory or steel wheel rollers. Depending on terrain, climate, and expected truck traffic, the base may be built in multiple layers, a thicker foundation below and a finer layer on top to ensure maximum stability. Heavy rollers move back and forth continuously, increasing load-bearing strength and reducing the risk of future settling or cracking. This compaction phase typically takes 2 to 4 days, depending on road length and soil moisture. Water trucks operate ahead of the rollers to maintain optimal moisture levels, allowing soil particles to bind tightly and reach proper density. Throughout the process, field technicians monitor conditions using compaction gauges, vibration sensors, and laser surveying equipment, ensuring every measurement stays within strict tolerances.
Process at a ready-mix concrete plant. All concrete used on major road projects is produced at an industrial batching plant, where materials are measured and mixed with near-perfect precision. The process begins with transporting raw aggregates to the plant. Crushed stone, sand, and gravel are unloaded into inline storage silos using wheel loaders or conveyor belts. Each material is stored separately in steel or concrete compartments, depending on the facility's design. Most plants are equipped to hold 4 or more aggregate types, allowing precise control over mix proportions. Once stored, each aggregate is weighed using calibrated belt scale systems. These systems measure exact quantities based on pre-programmed mix designs for each batch. After weighing, the aggregates are transferred into a feeder bucket designed to fully discharge all material without leaving residue. Next comes water. It is supplied either from the municipal network or on-site storage tanks and measured using an independent water weighing system. The exact amount required is released into the mixer through free-fall pipes or high-pressure pumps with spray nozzles, depending on the plant configuration. At the same time, chemical admixtures, such as superplasticizers, accelerators, or retarders, are added. These are measured separately using dedicated dosing systems to ensure accuracy and prevent cross-contamination. With all ingredients prepared, they are loaded into a high-performance concrete mixer. Depending on project requirements, the plant may use a pan mixer or a twin shaft mixer. Both systems provide rapid, uniform blending, producing high-quality concrete in a short cycle time. Once mixed, the finished concrete is discharged directly into ready-mix trucks waiting below. Timing is critical. Concrete typically remains workable for only 1 to 2 hours before it begins to set. During transport, the truck's rotating drum keeps the mixture in constant motion to prevent segregation or premature hardening. The trucks then head straight to the paving site. Laying concrete with a paving machine. When a truck arrives at the site, concrete is discharged into the receiving hopper of a slipform paving machine using a chute or powered conveyor. This step requires precise coordination between the truck driver and the paver operator to maintain a steady, uninterrupted flow of material. On long highway projects, multiple trucks operate in rotation, one unloading, one arriving, and others queued to ensure continuous paving without delays. In modern setups, conveyor systems connect directly from the truck to the paver, speeding up transfer and minimizing material loss. Once inside the machine, the slipform paver automatically spreads the concrete across the prepared subgrade following the exact width, thickness, and elevation specified in the design. No additional rolling or manual leveling is required. Inside the machine, vibrating pans and a forming mold compact and shape the concrete while it's still wet. An internal auger continuously moves the mix forward, distributing it evenly before it enters the mold. Laser sensors, GPS guidance, or 3D control systems ensure the finished surface remains flat, level, and perfectly aligned. As paving continues, the machine automatically inserts steel dowel bars from onboard storage. These bars are placed at mid-depth across the width of the road, allowing loads to transfer smoothly between slabs and reducing the risk of cracking at joints. This process is fully automated and does not interrupt paving, even on curved or winding sections. Thanks to its continuous slipform movement, the paver creates a seamless, monolithic slab with no cold joints, resulting in a stronger and more durable roadway. Depending on size and automation, these machines can cost anywhere from $120,000 to over $300,000, and they have become the global standard for large-scale concrete road construction. Curing, joint cutting, and final inspection. Immediately after pouring and initial curing, a liquid curing compound is sprayed over the concrete surface. This coating locks in moisture, preventing rapid drying and allowing the concrete to gain strength gradually. A few hours later, once the concrete begins to harden, workers use precision saws to cut expansion joints at regular intervals. These joints allow the pavement to expand and contract with temperature changes, preventing uncontrolled cracking. After cutting, all dust and debris are cleaned from the joints and a flexible sealant, typically polyurethane, silicone, or bitumen, is injected. Once pouring and initial curing are complete, traffic lanes are marked, warning signs are installed, and the road is closed to all vehicles for at least 7 days. This curing period allows the concrete to reach its designed strength without disturbance. Finally, site engineers conduct a full inspection, including compressive strength tests, surface flatness checks, and uniformity evaluations. Only after passing these quality controls is the road officially open to traffic.
Building concrete roads by hand. While concrete paving machines are standard across the United States, many developing countries, such as Peru, still rely heavily on manual road construction. Instead of slipform pavers, concrete is poured directly from mixer trucks through metal chutes. Workers then spread the mix by hand using shovels, rakes, and long screed boards. Dozens of laborers must coordinate in real time because even short delays can cause the concrete to begin setting before it's properly leveled. After the initial placement, handheld vibrators are used to compact the concrete, forcing out trapped air and increasing strength. Other workers follow closely behind, smoothing and texturing the surface with steel floats or hand rollers. Every step depends on experience and on-site judgment. Without laser guidance, sensors, or automated leveling systems, achieving precise elevation and surface flatness, especially over long distances, is extremely difficult. Yet this labor-intensive method remains common in remote or low-budget regions where modern machinery is unavailable. It highlights the stark contrast between high-tech automation and traditional hands-on infrastructure building. Road construction in China's harshest environment. Now, let's move to China, a country known for some of the most advanced infrastructure in Asia. What makes this project extraordinary is where it takes place, deep inside one of the hottest and most unforgiving landscapes on Earth, Taklamakan Desert. The first challenge is creating a stable, flat surface on shifting sand. Hundreds of bulldozers are deployed to reshape massive dunes, cutting down high ridges and redistributing sand into low areas. The objective is a smooth, balanced foundation capable of supporting heavy construction equipment without collapse. Surveyors constantly monitor elevation and slope, ensuring uniformity across miles of open desert. Conveyor systems remove excess sand from the work zone, while compactors gently press the surface to form a workable base. Even after leveling, loose desert sand cannot support construction. Engineers discovered that controlled moisture injection could stabilize it. Using long sprinkler arms and underground piping, groundwater is sprayed evenly across the surface, allowing moisture to penetrate several inches deep. Once the sand reaches the ideal dampness, heavy rollers move in. Pass after pass, steel drums compress the surface, eliminating air pockets and locking grains together. The rumble of machinery echoes across the desert as shifting sand transforms into a firm, uniform base. Under the intense desert sun, the surface dries and hardens, strong enough to carry cranes, mixers, and supply trucks, a foundation built almost entirely from sand and water. Building up the roadbed. With the sand stabilized, workers spread a base layer of soil over the surface. Dump trucks unload reddish earth, which bulldozers distribute evenly across the site. This added weight strengthens the sand below, preventing movement under heat, vibration, and traffic. Each section is carefully compacted, forming a dense and stable roadbed capable of supporting the next stages of construction, even in extreme desert conditions. Paving the desert highway. At the edge of the desert, portable asphalt plants roar to life. Stone, sand, and polymer-modified bitumen are heated to nearly 170 degrees Celsius. Insulated tankers deliver the hot mix non-stop to paving machines waiting on site. Each paver lays asphalt in layers about 6 centimeters thick, while rollers follow immediately, compacting the surface before it cools. The process unfolds like a synchronized operation. Initial passes use heavy steel drums for deep compression. Final passes switch to rubber tire rollers, sealing microscopic air gaps and smoothing the surface. Thermal sensors monitor asphalt temperature in real time. If it drops below 140 degrees Celsius, rolling stops instantly to prevent cracking. Once cooled, supervisors check flatness using laser systems, allowing no more than 3 millimeters of deviation per meter. As desert winds sweep across the site, the asphalt hardens into a flawless black ribbon, engineered to withstand temperature swings from -25 to +70 degrees Celsius. To finish, workers apply a protective seal coat, locking out moisture and giving the road its deep, reflective sheen. By dusk, the highway glows beneath the setting sun, a dark mirror cutting through an endless sea of sand. A road through the sea of death. After 4 grueling years of construction, the 4-lane highway crossing China's largest desert stands complete. What was once empty wasteland is now a vital transportation artery, a testament to human endurance, engineering precision, and technological mastery. The project not only connected distant regions of Xinjiang, but also demonstrated an achievement so remarkable that even international engineers took notice. That brings us to the end of today's video. You've seen how roads are built, from manual concrete work in developing regions to high-precision mega projects in China's harshest environments. All information was gathered from reliable sources. If you notice anything inaccurate, feel free to leave a comment. Thanks for watching, and we'll see you in the next video.